is on polynomial functions and their graphs. Now, so we're going to talk about what is a polynomial function at all, what are some characteristics of polynomial functions, and then we're going to put that all together to be able to draw the graphs. I know you have a graphing calculator, and I know that it will draw you the picture, but the problem when you get to a polynomial graph is sometimes you can't see the whole picture. We call that a complete graph. And so with some of these ideas that I'm going to tell you, it gives you a better idea about whether you've got the whole picture or not, or you need to change your viewing window so you can see more of what's going on to make sure you have the whole picture. So the first thing we want to be able to do is actually just identify it. Is this a polynomial? Okay, so polynomial functions are always of a certain form. F of x is equal to some number, I'm going to call it a sub n. There's going to be a number times a variable raised to a power. We're going to call that power n right now because I don't want to put a number in there. Okay? And then, if they're in the correct descending order, then the next power is one less. And this term is just another constant. And it goes all the way down to a constant term, where the power on the exponent is going down by 1 every time. Now the thing that makes it a polynomial is that n, and all the subsequent n's, where as it goes down by 1, has to be an integer. N is a non-negative, so it can't be negative either. So it can't be like the square root of x. That's not an integral exponent. It has to be like x to the first power, x to the second power, x to the third power, x to the fourth power. It's got to be just an integer. Y'all know what an integer is, right? And it can be like -2 or -4 for it to be a polynomial. Now, we can have those things, but they're not considered polynomials. We've already talked about some polynomial functions. We've got the one where it's f of x is equal to just some number, right? That was a constant function. Y'all remember that one? That's y equals a number. You know, it's a horizontal line. And then we have the ones where it's f of x is equal to some number times x to the first power, right? If you don't have an exponent, x is automatically to the first power. This was called what? If x is to the first power, it's called what? Linear. And what's an equation that's in this form called? Quadratic. Okay, those are the ones we've worked with. In this section, we're going to be talking about polynomial functions that have a power of 3 or higher. Now, when we talk about this stuff, we do need to look at, here my formula, this term right here, which is the term that's got the highest exponent in it, is called my leading term. My leading term tells me the degree, because the degree of the entire polynomial is the degree of the highest term. So the degree of this particular polynomial is n. And it comes out of the term that's got the highest power. And it ought to be at the beginning if you've got it in descending order like you're supposed to. And then this A sub n is called the leading coefficient. And there are a lot of things that we can tell about this particular function if we can look at the leading coefficient. Okay, so those are the things that you're going to be looking at when you look at this, is you're looking for the leading term because it tells you the degree of the polynomial, and the number that's attached to that is the leading coefficient, and it tells me a whole bunch of information about the look of the graph. These polynomial functions, their main characteristics, that they have smooth, continuous graphs. Okay, continuous does not mean that it goes on forever, right? We're not talking about continuous as in English, we're talking about continuous as in math. Can anybody remind me of what the word continuous means from mathematics? Has no break in it. Has no break in it. So in other words, as I'm walking along, there's never going to be a hole or an asymptote or anything else that we've talked about in this graph, right? There's no ending point. It's just a nice, smooth, continuous curve with no gaps. So, first thing, or the third thing that we want to talk about here is the end behavior. But this is our first application of that information I was telling you that we needed from this leading term. Okay, so when we look at the end behavior of the graph, now everybody know what end behavior means? What does end mean? At the end of something. Okay, so in other words, if I'm looking at a polynomial graph, then I'm talking about what's happening out here, not in the middle, out here on the ends, way out here as I get to a negative infinity and a positive infinity, what's going on. Okay? Everybody understand? Doesn't apply to the middle, just applies that at the end. The end behavior is based solely on the leading term. So when we get a polynomial and we look at this, we are just looking at that leading term. I like to organize it this way. On the leading term, or the degree of the polynomial, remember we called that n a while ago. N was the degree of the polynomial, right? That's the exponent. If n is an odd number, everybody knows what odd numbers are, right? 3, 5, 7, okay? And a sub n, which is the leading term, right, the number in front, is a number that's greater than 0. What does that mean to us? It's positive, right? It's a positive number. So the leading term's positive. Then what happens here, I'm just going to draw a piece of a graph here, is that these graphs are always going to start down or fall to the left. They're going to do some turns here in the middle, but they're going to end up shooting off into a positive infinity. Okay? So the author's way in this book of notating that is he does this. Falls to the left, rises to the right. That's his little shorthand for that. Okay? Everybody understand that? If n is odd, but a sub n is less than 0, so it's a negative number, then it does the opposite thing. It's going to start up. It's going to do some turnaround stuff here in the middle, nice smooth curves. We don't know what it's doing, but it is going to wind up falling to the right. So it starts up, ends falling down. It rises to the left and falls to the right. Okay? Now, the degree doesn't have to be odd. It can be even, right? So if a sub n is greater than 0, then what happens is it starts up, does some stuff in the middle, and it finishes up. Okay? Got it? And if it, yep, starts down, does some stuff in the middle, ends down. So checkpoint 1. They want us to determine the end behavior of f of x equal to x to the 4th minus 4x squared. Determine the end behavior. Remember, I look at just the leading term. So which one's the leading term? X to the 4th. The exponent is what I look at first. Is that an odd or an even number? It's even. So the degree is even. And is the number in front of x, which happens to be no number up there, so what is it? Positive 1. So it's a number that is greater than 0. So that means that it's going to start up and finish up. Or the way the author writes it is he says it rises to the left and rises to the right. That's all there is to it. On the test, I have seen this. Okay. The little arrows help you come up with this answer. Because if the arrow's pointing up, it's rising, and if it's on the left side, it's rising to the left. You know what I'm saying? I personally would do the arrows for myself to help me so that when I start writing the words out, I wouldn't get those backwards. Okay. Checkpoint 2. Wants us again to determine the end behavior, but this time of f of x equal to 2x to the 3rd times x minus 1 times x plus 5. Now, where is my leading term? No. Remember, for it to be a leading term, I have to have it so that it's in the form of some number times x to a power plus or minus some number times x to a power plus or minus some number times x to a power. Is this in the right form? One thing I could do is I could like multiply it all out. Do I really want to do that though? No. What am I going to be doing? I'm going to be multiplying these together, right? So number 1 on all of these terms here that are the leading terms, that's a 2, a 1, and a 1. So when I multiply that together, a sub n is 2, right? Everybody get that? I just took the numbers here in front of the x's because that's going to give me my leading term. Right? Multiply it all together. Now I need to know if n is even or odd. How did you get that? What's the degree of this one? 3. What's the degree of this one? And what's the degree of this one? When I multiply exponents, when I multiply like bases that have exponents, what do I do to their exponents? I'm adding them up. So n is 5. So it is odd. Very good. Okay? So just knowing that without having to go through and multiply all that junk together, what do I know about this end behavior? It's positive, n is odd, and a sub n is greater than 0, so it starts down but ends up. Okay? So that falls to the left, rises to the right. Okay? You do need to memorize those 4 sets. What? Up and up? Where'd it go? There it is. No, because one's got to face left and one's got to face right. So they're never going to go the same direction. I understand what you're asking me now. Sorry. All right, and checkpoint 3, the last example of this in behavior. They want us to find the end behavior of f of x equals negative 0.27 x to the third plus 9.2 x squared minus 102.9 x plus 400. But remember, what am I looking at? If I'm wanting the end behavior, I'm just looking at the leading term. So is this exponent even or odd? So it's odd. And is my coefficient that goes with that one with the highest exponent, is it less than or greater than 0? Less than 0. So you look back at your little chart that I gave you, and you'll see that that means that it rises to the left, falls to the right. Okay? So don't let that throw you off just because it gives you ugly numbers. Remember, if I'm wanting to know about end behavior, all I need to know is what's the degree, is it even or odd, and what's the coefficient. Okay? Any questions? That's not multiplied. That's added. The reason I added up here is because these were multiplied together. Okay? Good question. Okay. Now, get your graphing calculators out. NY equals, I want you to type in x to the third plus 13x squared plus 10x minus 4. Oh, darn it. Yeah. Gotta press what? Now delete's gonna push me down. Okay, thank you. Plus 13x. Anyway, type it into your calculator. Go to the Zoom and go to standard window and hit enter. And look at your picture. Okay. Now, I want you to look at that equation. F of x, this is checkpoint 4 by the way, f of x is equal to x to the third plus 13x squared plus 10x minus 4. Tell me what the end behavior ought to be. It's odd and positive. It ought to start down and end up, right? Does your picture on your graph start down? Does it fall to the left and rise to the right? So do you have a complete graph? No. Okay? That's what I'm telling you. I know your calculator will graph these for you, but sometimes you don't have the window big enough where you can see all of the graph. So that's why you need to memorize this, and you need to know what the end behavior needs to be so you can see if you've gone far enough out that you can see everything in the middle that you need to see. Okay? All right. Now there's another piece that goes with that. There's some more pieces that go with that. The next thing that we talk about is being able to find the zeros of the function. What does zero mean? Okay. The intercepts. But it's the x-axis, the x-intercepts that we're talking about. When we talk about zeros of the functions, that's where the function value is 0, which are the x-intercepts. Okay? So if you have an equation or a function, f of x is equal to x to the third plus 2x squared minus 4x minus 8. Then to find the zeros of the function, what that says is I'm going to say 0 is equal to this. You just spent a lot of time in Chapter 2 learning how to solve this equation. What do? Called factoring by grouping. Remember, if there are 4 terms, factor it by grouping. There's an x squared that's in common here. That leaves the x plus 2. There's a negative 4 that's in common here. That leaves x plus 2. Then once you factored the first time, you turn it into 2 terms that also contain a common factor of x plus 2. So I can factor those up front. And I get left x squared minus 4. And I'm hoping that you recognize that x squared minus 4 is the difference of 2 squares. So that turns into x plus 2 and x minus 2. Right? And so my zeros, the places where it's going to cross the x-axis is when x is equal to negative 2, when x is equal to negative 2, and when x is equal to a positive 2. Now, did you notice that I have the same x twice? Okay? That's something called multiplicity. Objective 5 deals with multiplicity of zeros. That actually means something to my graph. If a zero appears more than once, then it's got a multiplicity. So this one has multiplicity 2 because it's there twice. This one's got a multiplicity of 1 because it's just there once. Okay? Now, the way multiplicity works and how it has to do with my graph is that zeros with even multiplicity. So again, 2, 4. Touch the x-axis and bounce off. In other words, so if it's above the x-axis, it'll come down, it'll touch the x-axis at that point at -2, and it will bounce off and go back up. It does not cross through it. Zeros with odd multiplicities cross through the x-axis. Okay? That's kind of an important idea because it gives me an idea of the shape of the graph. So what this says to me is that I'm going to take, at x equals -2, I'm going to bounce off the graph, but when x is +2, I'm actually going to pass through it. Everybody understand? Okay. Objective 6. Oh, well, let me do objective 7. I mean, not objective 7, checkpoint 7, before I jump over and do objective 6. We want to find the multiplicity of the zeros of the function f of x equal to -4 times x plus 1/2 squared x minus 5 to the third. Now, a while ago, this one didn't work real well for me because I was looking at end behavior. But if I'm looking for zeros, if it's in factored form, my work's done, right? Because I take each one, set it equal to 0. So I'm going to have a 0 at a -1/2, right? Yes? And I'm going to have a 0 at a +5. Remember, it changes signs because I set it equal to 0 and solved for it. But at this 0, x equals -1/2, what's its multiplicity? Multiplicity is 2 because it's squared. That term is squared. So it means that 1/2 happens twice if I listed it out, right? And then this 0, x equals 5, has a multiplicity of 3. So what does that say to you in terms of the graph? Well, it bounces off at a -1/2, and it's going to cross over at 5. Good. Okay? Yeah? Up to you. 3 more ideas. Yep. Okay. So, the 6th thing that we've taught here is the intermediate value theorem. Okay? Intermediate value theorem. This is not a hard idea. Okay? It says that if f of a, now what does f of a stand for? The y value, right? Means I'm going to take some number, plug it in the equation, and I get a y back. That's what f of a stands for. And f of b means I took a different number and plugged it in the equation and got the y value back, right? So it says if f of a and f of b have opposite signs. Opposite signs means what? One's positive and one's negative. Okay, so if one's positive and one's negative, then at least one number, call it C, exists. They're just two different numbers. No, they're just two numbers and they just happen to give me back y values, and one's positive and one's negative. Then there is a C somewhere such that f of C has to be equal to 0. If I've got a nice smooth graph, and I had one x value that gave me a negative number, and another x value that gave me a positive number, then somewhere between there they had to have done what? Gone through the x-axis. There has to be some x value where the y value is 0. That's all the intermediate value theorem says. That if I've got an x and an x, one's a positive and one's got a negative y value, y has got to be 0 at some point between them. All it says. So don't let that hang you up. Okay, checkpoint 8. Where'd that go? Says if we have a function f of x that's 3x to the third minus 10x plus 9, we want to show that a real number a real zero, how about, exists between x equals negative 3 and x equals negative 2. Now, if we wanted to prove that, then we can prove that with this intermediate value theorem. This is how you do it. You do 3 times negative 3 squared minus 10 times negative 3 plus 9. In other words, you figure out what f of negative 3 is. Okay? And so that's 9, and 9 times 3 is 27, plus 30, plus 9. So that's 66. Right? Did I do it right? And we look at what f of negative 2 would be. 3 times negative 2 to the third. Oh, that's to the third. That's not right. Messed up. Because 3 to the third is negative 27, and negative 27 times 3 is negative 81, plus 30 plus 9. So it's negative 51, negative 42. Okay. And then this is 8. It's negative 8 times 3, which is negative 27, plus 20, plus 9. Did I say negative 27? Y'all knew I meant negative 24, though, right? Because 8 times 3 is 24. And so that's a positive 5. You've just proven that there has to be a real zero somewhere between negative 3 and negative 2. Because this one's negative and this one's positive. That's all there is to the intermediate value theorem. If they tell you to do that, that's all you do is you take one, plug it in, and then when you've got one positive and one negative answer, you have just proven that there's a real zero somewhere between negative 3 and negative 2. Then you have not proven it. Okay? So you say you cannot prove that there's a real zero between these two numbers. Might still be one. Sometimes in calculus we do a little bit of stuff where we get closer and closer together so we can try to find somewhere. Because what's happened sometimes is that you've dipped down below, but you're looking at so far out that your positives you're both positive. So you have to keep moving until you get one that's negative and one's positive. Okay? Turning point. A turning point is a maximum or minimum. You know, like on the quadratic equations, we got a turning point because it like dips down and goes back up, or it goes up and dips back down, like a vertex. Well, what happens with these polynomial functions is I have more than one of those. I can have several of them. And the way it works is that there can be no more than n minus 1 turning points for any polynomial function. So in other words, if you have a function that's like f of x is equal to 5x to the 4th plus 3x squared minus 4. Now, I don't know how many turning points there are for sure yet, but I know there cannot be more than 4 minus 1, which is 3. The most it can have is 3 turning points. May have fewer, but it cannot have more than that. So that helps you check to see if you have a complete graph too. Because, you know, if you look at that and you've got 3 turning points already, there's no sense in stretching it out any further, right? Because you've found all the middle stuff. You've got a complete graph. And the very last objective that's in here is just putting all this stuff together and actually graphing a polynomial equation. So objective 8. So checkpoint 9 wants us to graph f of x equal to x to the 3rd minus 3x squared. So first thing we talked about was that it was a nice smooth curve, right? So if I find some points, I'm going to be able to draw a line connecting them. We talked about end behavior. What end behavior does this have? It's odd and positive, so it's going to start down and end up. Okay? The next thing we talked about was zeros, right? So if I want the zeros, I'm going to say 0 is equal to x to the 3rd minus 3x squared. X to the squared factors out, and I'm left with x minus 3. Right? So x is equal to 0 with a multiplicity of 2, and x is equal to 3. Let me give you your assignment. Page 348, 3 through 72, multiples of 3. And you just go through here and you find these points, and you'll plot the points, and then you're just going to draw the graph.